no category at all. This stuff.
No, there were not many
Concrete numbers.
There were not categories, many categories in my
Okay.
talk.
Anyway, let's start. So, this is a kind of already known topic. Maybe I put some names. Yau, Hosono, Zudilin, Rivoal. And so there are many results that I will not mention. I will try to go to some part which I did with one of my postdocs some 6 years ago. Anyway, let's start. So let's take rational number A plus A. They are rational numbers. And generalized hypergeometric function. Let's define this one. This is A. There is a list of ones, so I will not put in my notation. But let's the classical notation is this one. It increase A1 until A, and there is this one also. It doesn't matter, just for the sake of completeness. But at the end of the day, what is this generalized hypergeometric function? It is just this series. A is equal to 0, infinity, A1 to the K, A2 to the K, AN to the K. I will now define it. K factorial to the N, Z to the N. And then I have to define this is the Pohammer symbol. AK is A plus 1, A plus K minus 1. So this is this is the generalized hypergeometric function, and there are parameters here, but I have set all of them equal to 1. I will just take care about these rational parameters. It is well known that if satisfies this hypergeometric equation, theta n theta plus A1 plus A2 theta plus An. So this guy applied to f is equal to 0, and theta is z, maybe z. Okay, maybe let's, before going to the main problem of this topic. So this is just one solution. This is a linear differential equation. It has many other solutions. One solution that also I will need in order to introduce the main problem is this logarithmic solution. What is this? This is FAZ times NNZ from function called GAZ. And this GAZ also in this context can be given a closed formula. And let's write it. Basically, let's say it is k equal to n at infinity. Here, you just put the same as this coefficient, and then there will be some extra. Let's say if I write it, I write the extra one, and g equal to 1, and I equal to 0, k minus 1, 1 a g plus I minus 1 plus I. Okay. Anyway, I will even it is I have when I copy from my own text to Blackboard. There's always some mistake, but at the end of the day, all this series has, let's say, a priori these are rational numbers, but in this case it will be integer. In this case also it is actually integer. But so let's finish the basic setup. Mirror map. So mirror map is just key exponential of the logarithmic f and then z plus g f, which will be at the end z times e to the g power. Anyway, up to some multiplication of the z with some integer, these guys they have integer. They are, let's say, formal powers with z coefficient. But the point is that if you make this combination, it still has z coefficient. But since if you write a Taylor series of exponential, since this has n factorial, at the end of the day, at most you can claim that this is a formal power series is in C. And the main issue of this talk is that for some very non-trivial reason, this guy also will have integer coefficient. And maybe I will say a little bit history about this one. This, let's say, the first, let's say, this example is famous: A1, A2, A4, 1, 5, 2, 5, 3, 5, 4, 5. This is the first example of a period computed in physics to do mirror symmetry. This is called mirror quintic. So there is a mirror quintic when you compute its period, some 3-0 form over some topological cycle, then up to some constant you land on this one with this parameters. And then in mirror symmetry you define the mirror map, you do computation, and then the results you want to count something, and there's still the counting problem that you have at the end. You get some integers, but just few coefficients. But there was no reason why this counting problem results on counting problem in the B model, which actually you don't count, you just compute something. And but anyway, I will not go into detail. But the integrality issues in all these counting problems in the B side of the mirror symmetry will reduce to the integrality of this Q in Z. And if this has Z coefficient, and then usually the people invert this one. They write Z in terms of Q, and then when you invert, then this natural numbers related to Gromov-Witten and so on will pop up in this way. Right?
Two questions. First is, for the logarithmic solution, it's unique up to a multiple of f.
Yeah, but then you see that this one starts from k equal to 1. So this means that it's already unique. So this is f ln z plus g. G start from order 1. So this means that, but f starts from a constant. So already you have killed this adding f to the logarithmic solution. Because if you add some multiple of f to g, then this term will not start from z to the 0. This will start from z to 0, not from z to the 1. Okay. So this is a.
But the log parts, is it well defined? Is it?
Which one? What do you mean by well, this is a statement. If you substitute this one and this one here, and then there are two solutions.
Right. You wrote down something, but just abstractly. If I don't know how to write down solutions.
Okay.
So
if you don't have just linear differential equation, there is the Frobenius method, it will say
So,
the structure of the solution in terms of holomorphic functions and log z to the square, and so on.
right, but that's just one way of writing down the solution.
Uh-huh.
I mean, just abstractly, the log solution. You said that it doesn't have ambiguity because I want G to have zero
Yeah,
confidence
that is the G
coefficients.
because
But
that,
how do you extract G from the log solution? So suppose tell you something.
no, you just if you extract it from the log solution, at the end of the day, what I'm saying that there is this well, this you know that the holomorphic.
You
This
already
one
have
and then this
that.
is something unknown, and this unknown also you can recursively compute from
Right,
the
right.
differential equation.
You already have that.
Anyway, I will not go to this this chromophytons stuff and so on, but one of the basic steps in proving the integrality of all these chromophyton invariant at the end is this integrality of the coefficient of this one. And the main, as I said, the main reason is that even so this one has integer coefficient, when you write down the Taylor series exponential, there is an n factorial that a priori will get, you have to get rational numbers for the coefficients. And then, but for some non-trivial reason, for example, here apparently it is rational, but really you can easy to verify that these are actually integer. After that is some multiplications with some constant. But here it is it's not easy, and then the story starts from for this one.
And the claim that for any choice of A in Q.
No, exactly. No, it's not A. For the moment, I'm just for example for this one. And the topic is exactly to classify A's such that this integrality holds.
Okay.
Okay. So maybe I write it this way. So when I'm saying integrality, it's always optimal finding some integer, multiply it with z, and then ask for the integrality. So this is the main. And then you will not see any group of iterate stuff here. Okay, so something all these people they have used, but they really didn't go to the maximum application of this method, and then I want to emphasize this one is exactly has to do with Dwork. Dwork, first of all, let's say the Dwork operator. Maybe I have first to find this one. So P prime, a rational number. It's a very simple operator on rational numbers. Is delta P A x. So if let's say P does not divide the denominator of x, so just assume that x doesn't have the denominator of x. So if you make the quotient of x by P, then the denominator will be there. But what you do, you add it here, x0, some integer between P minus 1, 0, such that the denominator, in the denominator of this rational number, P disappears. You can such that P doesn't divide the denominator of x. So there is a unique x0 between 0 and P minus 1 that if you make this one, there will be P on the numerator, and this P in the numerator will be cancelled with P on the denominator, and then at the end you will have something without P in the denominator. Okay, so So this is very simple. So something that in the oldies work doesn't pop up. Maybe I write as a conjecture. Okay, maybe if I have to one more definition. Okay. Definition. So let's check some formal power series in Z is P integral if P does not appear, if P doesn't appear in the denominator of the coefficients of F. So all this formal power series is just all the coefficients will be rational numbers where the P does not appear in the denominator. And then in the same, F is called N integral. If let's say if you multiply Z with N, this must have integer coefficient. Okay. So well, for this class of let's say for this Q, easy. Let's say this is an easy verification. Is that in our case Q is P integral for all P field over prime except a finite number. So then this is equivalent to say that Q is Q. This is the mirror map. Q is N. In general, it's false, but in this case, let's say this is Q. So if you prove that this Q is P integral for infinite number for all primes except the finite number, then really you can find this N such that that Q and Z becomes this has integer coefficient. This is mainly because of the structure that you have there. Okay, so let's go. So our main topic is exactly to consider an integrality. Okay.
What does 5 integral mean? The two definitions seem different. So if I say 5 integral.
Oh, okay. Yeah, exactly. You have to. Okay. Okay. There is a This is a kind of ambiguity in the definition. So let me. No, this is the point that everybody uses in this way. At the end, you don't substitute N.
You'll say N equals 5 integral or P equals 5 integral, something like
That's
that.
good. Let's start here. Yeah, even in Dwork.
Really?
I have to remember, but exactly there is a problem in the notation.
Oh.
If you put N equals to prime. Okay. Maybe let me. Okay, there are two conjectures. Let's. The main topic of the topic is this one. Q is N integral. Actually, there's a partial one using the P, but maybe if you want, let's just forget this one and just stay in the N integral one. If and only if. Maybe I write delta P A1, delta P A2 is equal to A1, A2, or 1 minus A1, 1 minus A2. This is for n equal to 2 and n not equal to 2. Then the set of delta P A1, delta P AN must be the same as A1, A2. This is for almost for all primes again except the finite number. So this means that if Q is going to be an integral,
Sorry. An integral means there is
some integer n, and when you multiply z with that n, all the coefficients of your Q, it will be an integer. So the case of n equal to 2 is a little bit different. This has to do with some equality related to hypergeometric function n equal to 2. But I will focus in the case of n equal to 4, 3, 4, 5, 6, and so on. So at the end of the day, this means that delta P, the Dwork's operator, must just permute the coefficient for almost all prime P. And yeah. So this is partially a lot of these works that by many people, they are always considered the special cases because the special cases were coming from physics. But in this generality, it is this kind of statement was never written. And then maybe I will try. Okay, maybe let's put the theorem also. Let's say, as I said, the ideas are already done by many people. But when you write in this format, maybe this. This is in my one of the appendices in my book. Maybe let's say this conjecture is doing n equal to 1. N equal to 1 is trivial. 2, 3, and 4. And really, if you really invest a lot, some part of the verification is done by computer calculation, but you can really go high. But I will say why what are the difficulties to settle down this one in general. Maybe a little bit I give some motivation. It has to do again with the classification of Calabi-Yau varieties, which is still a kind of very big open problem. Calabi-Yau three-folds or Calabi-Yau n-fold bigger than or equal to 3. Okay, I will focus from n. So, okay. Okay, so let me just focus on this. Let's say to this two case. Let me say maybe I have one observation. If you play a little bit with this trying to find rational numbers such that satisfy this one, you will observe that for n, let's go bigger than. Let's assume that we are always bigger than 3, but n odd. Okay, maybe in this way. A1, A2. Let's say n. Even if you have, let's say, this is, I have written this one as set, I will write this one as set. If you find such n tuple, then when you go to the odd number, then it is just A1, A2, AN, and then adding 1/2, and vice versa. So there is a bijection. And even, and then will be. So this means that now I'm talking about this side, okay? So if you have A1, A2, AN such that satisfies such condition, then this will satisfy such condition. And if you are in the odd case, A1, A2, AN, and AN plus 1, which satisfies such condition, you can prove that one of them is at least 1/2, and then you can go back to the to this case. So there is a bijection between A cases in the n even and n odd, which is you put n plus 1. So maybe this I will again back to this, but another thing that you will see that okay, there is odd primes, but actually you don't need odd primes. You can there is a way to say that which primes I have to look to classify these rational numbers. If you do this one and you put in the computer to classify all this, then this will give 14. There are just 14 cases, including the mirror quintic, including A equal to 1, 5, 2, 5. This is the most famous one. So what is this? There are just, for n equal to 4, there are just 14 set of rational numbers. That's why in this one. And then in this case, you will find 14 cases and so on. This 14 classification is a kind of famous, first done in a monodromy context by Morgan, Doran Morgan. But since then, there are many different ways to get this 14 class of hypergeometric function. And at the end of the day, all these 14 cases, something that I have to say, there are Calabi-Yau threefold, P1, and then you have to cut the singular fiber, and then delta T, and they will be all these 14 cases. F is just up to some constant, or the periods of the Calabi-Yau threefold. So this is Calabi-Yau threefold. So in some sense, what we are claiming that among these hypergeometric functions, only 14 of them are periods of Calabi-Yau threefolds, and rest of them are not, because we are expecting that any computation that the mirror map for any Calabi-Yau threefold, if you define it properly, it must be an integral, because it is supposed to count some Gromov-Witten values. So this is, for me, this is the first kind of classification, not of Calabi-Yau varieties, but the Picard-Fuchs equation of the Calabi-Yau varieties. And of course, there is you can go there. In each step, there are finite number. So I have to say that this n is n minus 1. Always n minus 1 is going to be the dimension of the Calabi-Yau. And for example, in the case of this n equal to 6, you have okay. So according, maybe we have let's go to the n equal to 5. So n equal to 6. According to this philosophy, n equal to 4, n equal to 5, and the 6 are the same. There is just the same set of rational number. So n equal to 5 must correspond to 40 class of Calabi-Yau fourfolds. And I just knew one or two of them, the geometric origin, but except one or two, the rest I don't know if somebody has constructed the corresponding Calabi-Yau fourfold. But a priori, there is going to be 40 families of Calabi-Yau fourfold with the Hodge numbers, and in all of them, the Hodge number must be just 1, 1, 1, 1, 1, all of that number. Okay, so I told this one because this at the end these things become the kind of classification of Calabi-Yau varieties, which is why this is difficult, and you classify the corresponding Picard-Fuchs equation, which in this case is this hypergeometric function. Okay, so let's return back to the main topic. Okay, so this side, as I said, most of the people that I wrote there, they were mainly busy with this side. So find for example, check 1 over 5, 2 over 5, 4 over 5, it satisfies this property, and then you get the integrality. And apparently nobody cared about this if and only if side, so this means that really you get an integrality if this happens. And this is a kind of now classical consequence of Dwork theorem that I'm going to write of this Dwork theorem. So maybe okay, I write, and then the difficulty of going back is exactly the, this restriction as is when you want to from here to here. So what is Dwork theorem? For me, this is one of the beautiful theorem. I don't understand. I have never. I don't understand its proof. I have not found any person who completely understands its proof, because anyway. But apparently, well, everything is okay. It works perfectly, and maybe I write works theorem. So it is a little bit more general than for hypergeometric function, but let's just stay in this way. So it is a very beautiful equality. You don't need too much to talk to explain it. Remember that we had this one. So apply the Dwork operator to A coefficients. You have G. Then apply again in the A coefficient in of F. You have this one. This is congruent to P, the prime P. Okay, there is, then make this Z to the P, Z to the P, G, A, Z, F, A, Z, and this is mod P. Now let's do in the p-adic stuff, Z, P, p-adic numbers, formal powers in p-adic numbers. So these two formal powers is considered as formal powers in p-adic numbers. The difference is always divisible by p, and yeah, this is the Dwork theorem that is mainly responsible for this part. And okay. So maybe okay, maybe I give you the rough idea of how you use this one to get this one. From this one, it's still a little bit work. You do a little bit work, and then you will get another. You will get this proposition. If so, something that here if Q. Okay, let's go to this P integral in the sense that just one prime P fixing the prime. This P integral. Then okay. Then G delta P A A Z F delta K A Z. This is congruent to G A mod PZP. So the point is that, okay, this theorem is general for any parameter A. But if you assume that Q is P integral, you can combine the P integrality of this guy with this theorem, get rid of this to the Z to the P stuff, and then you simply land on this kind of conference, which there is no Z to the P, but it's still delta P is acting on the coefficients, and the difference of this one with this one is always divisible by P. And something again a little bit working if
Where is Q? Where is Q in this case?
no, the Q is was this mirror map. Q is what the E Z is listed. Remember, Q was Z E to the G to the F. At the end is evaluate RZ. Okay. So okay, something also that we can conclude. If this guy is n integral, this means that it is P integral for almost all P's. Then here you have equality because the difference is always divisible by all P. And then if Q is n integral, then okay, now I'm not explaining this side. I'm trying to go explain the other side. But as I said, this side is a kind of a classical. So then a star is an equality. And basically why? Because you make the difference, it has rational number, at the end of these guys are rational numbers. You claim that it is divisible by almost all the primes, so it must be just 0. The difference must be 0, so you really get an equality. And okay. So, once you get there, then, and even if you are interested on, let's say, this part, which never the people touched it, this is I'm trying to a little bit explain this part. So you will. Let's just formulate the kind of again.
Sorry.
Huh?
So if it's an integral, then you run the same thing for all P.
Yeah, all P except the finite.
The left-hand side depends on P, so you don't have a fixed thing.
Oh, okay. So let me say. No, the argument is not complex. One has to argue about the.
You assume that delta P commutes all things for almost all time. You assume
No, I want to get from here to this. Yeah. The idea is that maybe I have. So the issue is that this also is in a finite. It's just there cannot be any number. For the denominator of these guys is already bounded. I mean, for example, if you fix A, then these guys also have the same denominator, and then you can argue that this is going to be equality. But of course, just with one prime, since this guy depends on P, the one that I was telling it's not correct. Then you have to still argue further.
For a smaller but still infinite set of primes,
Yeah, yeah.
the left hand side is the same.
Yeah. Okay.
Now, which can you take? You get the equality.
Huh?
You need to choose the end, right?
I have to use that this delta P, for example, when acts on a rational number, at the end you have the same rational number, well, we have different rational number with this different denominator, and of course I cannot argue in general. For this one I have to use also the structure of the Dwork operator.
That just means the statement Q is integral. What's this then mean?
N is going to depend on some collection of some bad primes that you don't care about them. So the primes of N are going to those that, for example, in the case of mere quintic, it will be some power of 5.
That just means in order to prove the conjecture, you need to choose suitable set of N.
Yeah, exactly. In each case, for example, this, for example, the 14, well-known 14 case, you choose the people also compute this N exactly what N is supposed to be.
Can you give an example of this delta P?
Yeah,
What does it look like?
Say,
Small numbers.
huh? Okay, so let's say it is.
3 x plus x.
So this one, the prime, let's say the prime, let's say 3 here,
Yes.
then 2, 5. So I have to make, let's say 5 plus 2, 10 plus 2. Okay, this is 2, and this will be what? Then 5, 10, 10, 12, 12 with 3. This is 4, 14.
Over 5.
Huh?
Over 5. 4 over 5, the final number.
Oh, okay.
4
over 5.
Oh, yeah. Okay. So I have to choose something between 0 and 2, such that this guy has no denominator 3. This is it.
So this thing is bounded. The value is bounded with bounded denominator.
Exactly. This acts just on a rational number with bounded denominator.
Okay.
Okay. But okay, then. Okay, as I said that just with single prime you cannot claim, but because of the structure of delta P at the end you argue that there must be an equality, and then you will land on a very concrete problem. Let's say that. I mean, let's say I write it a kind of conjecture because that one will depend on this one. Again, let's consider the case n not equal to 2, because n equal to 2 the story will be different. A, B, and Qn. So just take two class of two hypergeometric function with different parameters, and so and assume that they are equal. So this must imply. So the point is that in this generality it turns out to be false. But let's consider our case. But at the end there is some commutative algebra going on. So if these are equals, then this means that the set of A1, A2 must be the set of E1, E2, En. Because at the end I argued that this will be usual equality. Now I have get a situation like this. I have two hypergeometric functions. One is with B parameter, the other with A parameter. Suddenly they're, let's say, let's call this one also the, okay, it's a mirror map. But anyway, these quotient are the same. And then you claim that it is, they are the same. Okay.
A1 up to
Huh?
A1 up to
Oh, sorry. So the set of A and B must be the same. At the end of the day, this hypergeometric function is just depends on the set of AIs, not the order. This is here we typically write order, but it is not. It doesn't depend on the order. Okay, and this is the main part that really the other. So if one solves this one, at least for the any bigger not equal to 2, then the other conjecture is already solved. This means that you classify all hypergeometric functions, which probably comes from Calabi-Yau n-fold, in this case Calabi-Yau n-1 fold. And as I said, there are 14, 40, and then and increasing the number of cases increases, even though you don't know what is the corresponding Calabi-Yau. Okay, so let's just a little bit focus on this one.
Do we know if it's finite or infinite?
Yeah, there's a generating function. Okay, maybe if the generating function is very nice. Let's just look at the generating function. The case of 2 you have to discard it, but basically the generating function is this one. M equal to 2, infinity, 1. Was that 1 minus x to the phi to the m. Phi is the Euler's phi function. So the coefficient, nth coefficient of this guy is an integer which counts the number of AI with such property. This is what images that you have a finite number of objects. Okay, so maybe let's just skip the. For now, just imagine that this guy, A's are variables. Just imagine they are variables, and at the end, if you imagine and you consider them as variables, then you will see that this guy is something like this: k equals to 1, infinity, ck, a, z, n, and this ck, a is a polynomial with rational coefficients in A. If you just look up you look at the structure of G and F, then even you can implement in computer, and then you can take A as variable. This CKA is just a polynomial in A. So it is, since, well, I don't know how to theoretically handle this thing. If you have some ability with computer, you say that, okay, I have ideal generated, you define this ideal generated by CKA minus CKB. Now, you consider 2 class of variables. So this ideal is inside the QAB. And then the idea is that the 0 set of its ideal, of course, you must be careful with the restrictions. Just must be, how to say, it must come from the permutations. And okay, maybe I will just try to write one statement at least. What is the most for the zero set of this ideal, at the end you are interested which variety, this one equal to this one. This is a variety given by AI equal to some bj. Okay? And it turns out that this variety, even for simple extraction, might have other components rather than the expected component coming from here. Maybe. What I am saying, so this is a zero set. Okay, so let me. So okay, I didn't tell what is m. M equal to 1. M is at the k equal to 1, 2, m. Okay, I am considering the ideal generated by all these guys. By Hilbert-Nourish-Milstead, I know that it is finitely generated, but at the end in the computer you can't put all of the polynomials at the same time. So you said that, okay, I will take the first m polynomial, okay? And for m very big, the expectation is that this ideal, let's say the primary decomposition of this ideal must be, let's say, okay, I write it. If let's say right in the geometric context, if the zero set, it is Bin equal to, let's say, A1 minus B sigma 1, this, let's say this zero set of equal this A2 minus B A(n) minus B sigma n equals to 0. If I find what I'm saying, if okay, actually the union of all these guys, or all sigma, a paired notation of 1, 2, n. If I prove that the zero set of this guy is just this guy, this means that at the end, if I have this equality, then I can conclude this one.
That's arithmetic equality. You actually mean that they are the same after permutation. Because the set being the same could be a half, a third, a third, a half. They're the same set. But
the point that now I consider just this one as variables. Okay.
No. But I mean, do you really mean they're the same as sets?
No, they're the same as the set. Yeah.
But a half. So let's say A is a half, a third. B is a half, a third. That
okay.
shouldn't qualify.
Okay.
Okay.
No, I want maybe this one. Let's maybe exactly. We're going to have to write down this.
Which one do you want to? Which one of the condition that you want to use here?
What?
There are two conditions. One is they're the same as the sets. The other is they're the same after permutation. Which one is the one that you want to put here?
Which one I want to put here? No, I need that they are the same as the set.
The set.
So this means that the algebraic variety here, let's say the algebraic variety. Given by A1, B2, AN, B1, B1, BN. At the end of the day, this has many components, and when there are equalities between the elements, there will be some another components the variety that you were telling. If there the repetition, this will be give some some order components. But at the end, this is a union of many components. Right. And so maybe okay. So the point is that really even a little bit, even in this general context, it is hard to get something with computer. So the point is that if you're trying to solve in this computer, what you will do, you will fix M, and what is the you will try to compute the component of this guy. What are the algorithm for computing the components of variety? Instead of variety, you have to look to the ideal, and there is this primary decomposition. There are many primary decomposition of an ideal. So there are many algorithms for this one, and in many simple cases, really you are able to do it, but in many other cases, I have to return back to the structure of this delta P. For example, one of the affirmation that I did, when n is odd, one of them must be 1/2, 1/2. This means that at least you can reduce the number of variables by some by studying the structure of delta P. Something, for example. So this, in general, it will just work for our purpose. It will work for the in the case of n equal to 1 or 2. Maybe some observation which again reduces. Okay, that's it.
Over there, you wrote V of that ideal is equal to that thing.
Huh?
You wrote V of that ideal is equal to that algebraic
So
variety.
if then you are done.
But here
it is not true.
it's not.
But this is not true.
You can't.
This is what I'm saying that.
It can't be, because in the conjecture it only says one implies the other one. In the conjecture, it only says one thing implies the other thing. The other way around.
No, the other way around is it's a classical.
Classical.
All these people that if you have this delta P equal to that.
No. This.
No, there is no other way around here. But the other way around is the trivial. If you have this equality, this is already trivial. Because this.
For a half, a third, and a third, a half.
No, F just depends on the set B.
No, it also depends on how many times a number appears.
Yeah, okay, but what I'm saying is at the end, okay, then you have to be very careful because what I'm saying that, then the number of repetitions also, the number of repetitions of n element also, it is, you have to consider here.
Oh.
So maybe, okay, then about the number of repetitions.
Okay.
Like this is.
Okay.
Number of repetitions. This after you have to count also.
Okay.
So it is okay. It is not just the equality of the set,
Okay.
but n set with n elements, and then each element has some number of repetitions, such that at the end you have n in total n elements, or maybe you associate multiplicity to each. Okay, so this means that at the end of the day, when you really work out this one, this is not true. But the point is that, well, this was a little bit general. This P at the end is going to be the Dwork. Then you have to a little bit work with this general with AIs, for example, n even. For example, in this case, for example, if you look this Dwork operator, you will find out that, let me say, how I want to say, Q integrality. Let's say Q A Z. This Q integrality will imply that A1, A2, then you have let's say and even let's say 2M and well, but the point that exactly it's not a set, it is not just ordered also, so it is a set with multiplicity, but let me just write it. So something that reduces the number of variables you in your the problem that you have, one of them is this one. If you have the Q P an integrality, your set A and N is even, then there are half of them that you don't know, but the other half is just 1 minus the first half.
That's the n integral.
And that is, yeah, exactly, n integral. And then what is the moral of the story? This means that at the end, you can, this commutative algebra problem is much more difficult if you put more and more variables. Then at least you can reduce half of the variables, and you have less complexity. And even in the case of n equal to 4, we had to use once again a little bit the structure of the delta p. So this follows from the structure of delta p. One has to use again a little bit to reduce the number of variables, and then at the end one can prove something like this. So. Okay, then well, maybe I will stop it here. So maybe the moral of the story is that, as I said, there is no classification of Calabi-Yau varieties, but it's still in the level of Picard-Fuchs equation. One can try to classify Picard-Fuchs equation, linear differential equation, which probably come from Calabi-Yau varieties, even you don't know geometry. And all these techniques are more, let's say, kind of formal properties, Dwork theorem, helps to a little bit understand what would be this general problem of classification of Calabi-Yau varieties. Okay, so just this. Any question?